So hi everyone. Before I get started, just want to give a shout out to the organizers for putting this event on. A lot of awesome talks coming up, so really excited to be here. And so yeah, let's get started with some introductions. So you may notice I did this work with my colleague Daniel King. He unfortunately was not able to make it today. He's currently supporting Pwn2Own for Microsoft, which unfortunately is conflicting with this conference. But I just want to give a quick introduction for who he is. So he's the one who pretty much started this project up. He has a lot of security background. He's currently in MSRC at Microsoft, so they kind of handle the external cases that are coming in, triaging that, and also he gets to do a lot of cool research. He was a prior member of the Keen Security Lab. He participated in Pwn2Own back in 2016, and he was a member of the Master of Pwn. Also gave a lot of presentations on fuzzing. And for me, so my name is Shawn Denbow. I've been in security for a little bit now. Got my start while in university playing mostly Capture the Flags and war games. College was expensive, so I had an Air Force scholarship. So after I graduated, did 4 years active duty in the Air Force. About October 2017, I moved on to Microsoft. And I was doing security for a while. Up until about a month ago, I switched over to a software development role, so working on the kernel. So a quick overview for what this presentation is going to be about today. So it's really structured in two parts. The first half of this presentation, we're just going to lay out the groundwork and present the fundamentals. We'll go over the Hyper-V architecture, really from a high level. We're not going to go too in depth. We'll discuss hypercalls. This is what we're going to be attacking today. And then in the second part, we'll actually discuss the fuzzer that we developed and talk about some of the findings we got from this technique. So the first question, why hypercalls? Why was it that Daniel and I chose to attack these? And it really boils down to the fact that we were both new to the Hyper-V space, and as we started to ramp up and learn a little bit more, one of the things that stuck out to us was this interface that is exposed to a guest. So think of it as the virtual machine. And the interesting thing is it's accessible from ring 0, so from kernel mode, and from our perspective, this is a clear security boundary and an obvious attack surface. So we wanted to keep digging a little deeper. And additionally, hypercalls, they touch a number of facilities within the hypervisor. So it was really a natural starting point for us to learn kind of more of the internals and understand what's going on. And additionally, the Hyper-V dev team, they produced this document known as the top-level functional spec, or TLFS for short. And this goes in great details on a number of those facilities, as well as documenting the interface of what the hypercalls are, and they also kind of document what the arguments are. And we'll get more to that later. It's also worth pointing out that Daniel and I, we started this work separately, so if you notice, we both are on two different teams. And when I got started, I was just doing pure code review. That's how I generally like to do my bug hunting. And it was through a meetup. I usually bi-weekly get some drinks with the MSRC Redmond crew. So I was talking about some of the work I was doing, and shout out to Axel, who told me about the work Daniel was doing. So Daniel was already fuzzing, and he also had some pretty early results. So we kind of teamed up, and we looked at different scenarios for how we can get this even further. So the next thing, why is it that we, Microsoft, are here presenting this work to you? So in short, we're very motivated to secure Hyper-V. It's critical work, and the work in order to do this, it's non-trivial, and the external research community, you guys have the skill set necessary to do it, and that's why MSRC offers up this bug bounty. So they'll pay up to $250,000 if you provide a working exploit, but more interesting, if you can provide just a provable bug that shows remote code execution, you don't need to exploit it, we'll pay up to $200,000. And additionally, I believe it's important for us to be transparent about the work we're doing. So if we expect external researchers to contribute to this, I think it's worthwhile so we can explain what efforts we went through so you know how to differentiate and find additional bugs and identify gaps that we may have had and earn this bug bounty. So as I mentioned in the overview, this next section coming up, it's not going to be a deep dive into the full architecture. This has been presented in multiple past presentations, and there's a lot of resources online. I have an appendix at the end of this slide deck for people who are interested. But really the purpose of this section is just to provide a summary for those that might not be familiar with this space and kind of ensure that our terminology is right. So here we have a diagram of the high-level architecture of Hyper-V. And when you first look at the architecture, one of the things you'll notice is that Hyper-V's hypervisor is a type 1 or native hypervisor. This essentially means that it runs on bare metal. The hypervisor is essentially a small microkernel, and it provides a number of services to these things called partitions. And these services include things like scheduling virtual processor, memory management, and interrupt delivery. The hypervisor also handles hypercalls, and that's pretty much what we're going to be talking about today. And these hypercalls, again, they're just an interface that's exposed to the guest in order for a partition to communicate with the hypervisor. So partitions, they're the main isolation unit that's basically composed of some physical memory. You're going to have one or more virtual processors. And the hypervisor is ultimately responsible for managing what's known as the nested page table or second level address translation. And essentially what this does is it allows the hypervisor to enforce physical memory restrictions between these partitions. So this way we can guarantee that one partition, so if you have a VM in Azure, they can't read whatever you're doing or manipulate or bring you down. So in this architecture, we have what's known as the root partition. This is also commonly known as the parent partition. And the root is the host operating system. And right now we only currently support Windows. And the root is the only partition that has direct access to physical memory and devices, and it's therefore ultimately responsible for managing the virtual machines. So it contains, if you zoom in on the root partition, it kind of contains what's known as the virtualization stack. And the virtualization stack has a number of different components. So if you look at the very top left, you have the VMWP, which is the virtual machine worker process. And the virtual machine worker process is the executable that's in charge of orchestrating the life of these VMs. And as you see, it kind of communicates down in this stack, so it talks with the VID. The VID is an important driver, as that's the virtualization infrastructure driver, and this is what manages certain partitions and other services provided. And it essentially wraps the hypercalls in order to make all this happen. So if we look, we have two types of child partitions. You have an enlightened partition and an unenlightened partition. An enlightened partition essentially means it's aware that it's running on top of Hyper-V. Sorry, these are known as virtualization service consumers, and these VSCs they kind of communicate with something known as VM bus. So VM bus is, in short, a virtual bus that essentially allows Hyper-V to offer up pair virtualization. It can create a channel between the host and these guest partitions and allow them to share data and also set up synthetic devices. An unenlightened partition, it's pretty much that. It has no awareness that it's running on top of Hyper-V, so it's a lot slower because now anytime we perform some type of hardware access, we're going to have to emulate it. So next I want to talk about a concept of nested virtualization. I'm not going to go too much into detail here. The main importance is to understand this terminology. So nested virtualization, in short, is essentially the hypervisor will now expose virtualization extensions, which is implemented in the hardware, to these guest partitions. And these guest partitions can now run their own Hyper-V. So from our perspective for fuzzing, this is fantastic because now I can run multiple versions of the multiple hypervisors on a single machine. So looking at this terminology, we have level 0. So that's going to be your bare metal hypervisor. And this is going to manage your level 1, which you have your root OS. So that's going to contain the virtualization stack, which manages its child partitions. And the child partitions can also now run their own hypervisor. And this is going to be known as your L1 hypervisor. And again, it just goes up one more level. So again, you have a root partition, which is now level 2. It has its own virtualization stack, and it manages level 2 VMs. So next, I want to introduce a more recent technology, virtualization-based security. So this is pretty cool. It was introduced in Windows 10, really in order to help combat kernel mode malware. Kind of came to the realization that you're always going to get owned, so we started looking for different solutions. And so with VBS, it takes advantage of virtualization technology to essentially create a new security boundary, and we're going to refer to this as virtual secure mode. So the hypervisor introduces this notion of virtual trust levels. And the main idea here is that a higher numbered trust level is going to have more privileges than a lower leveled. And the virtual trust levels are represented as an attribute associated with each virtual processor. So within VSM, each virtual processor is going to maintain a running trust level. And this particular trust level is going to be referred to as your active VTL. And when running, the VP can only access memory that is configured for that trust level. And these trust levels, the way they get these memory restrictions, I hinted to it earlier, they use nested page tables or that second level address translation. So they can essentially program this to wall off portions of memory. You also have the concept of the IOMMU, which stands for the IO Memory Management Unit. So this provides services like DMA remapping and interrupt remapping. So if you have a malicious device, it can't perform DMA on a higher level trust level or another partition that it's not assigned to. So in VSM today, we currently only support 2 trust levels. So you have VTL 0 and VTL 1. VTL 0 is what's called normal mode, and this is what contains the normal NT kernel, and this is what the user interacts with. VTL 1 is the secure mode. And so you see we have this concept of a secure kernel, and really this is it provides very minimal functionality to these isolated processes, which are really just programs with walled off, so it contains some secrets. And what's interesting is, from a security perspective, this new security boundary that they set up, we want to find a way to break this. And one way to do it is with the services that the secure kernel provides. So it provides something known as secure calls. And as we get into this presentation, what we're going to realize is they're just a hypercall, and they have a different, same calling convention, but take a different format. So we'll talk about that in a bit. All right, so next I want to dive into understanding hypercalls. So here we're going to look at the basics. We're going to look at how we can set up an interface and actually invoke them. And also I'm going to talk a little bit about some restrictions that certain hypercall handlers might enforce. So some basics. So as I mentioned earlier, hypercalls are really just that main interface that's exposed to a partition in order for it to communicate with the hypervisor. And there are currently 3 calling conventions that are supported. So the first calling convention is the slow, or sometimes referred to as regular. And with this, basically your input and output buffers, they're going to be passed in and out of the hypervisor via 2 guest physical pages. And additionally, these input and output buffers, they need to be constrained to a page size and therefore must be aligned to a natural boundary. The second calling convention supported is fast. So here the input and output here the input parameters are going to be passed in using general purpose registers. And currently with this calling convention, it only supports passing in up to 2 or fewer parameters, and there's no output. So if you have a hypercall that has some type of output, you can't use this calling convention. So this calling convention is much faster, which is why it has its name, because there's no memory allocations or mappings involved. The third one is very similar to fast. It's called XMM fast. And essentially, if your processor supports the XMM registers, you can use up to 6 of the volatile ones to provide 112 bytes of input. And additionally, you can utilize these for output as well. So next we have the hypercall classes, and we have 2 of them. So you have your simple and repeat. So a simple hypercall simply performs a single operation. The hypervisor tries its best to ensure that it will complete a hypercall within 50 microseconds. So for some that perform more complex operations, they bring in this notion of repeat or continuation. So basically it makes it so the caller can invoke a hypercall, say you wanted to map a bunch of pages in, and it only processed half of them. So it's going to report back that it only processed half of them, and it's up to the caller to continue the process and give it a new index to start mapping the rest of the pages. Another topic I want to talk about is the variable sized hypercalls. So most hypercalls have a fixed size input, but there are a few that require dynamic data. And these variable sized hypercalls, they come in both simple and repeat. So both the simple hypercalls and repeat can support variable sized data. And the size is going to be specified within your hypercall input. So I kind of have what the hypercall input value is listed up there. And you see the variable header size. It must be specified as a multiple of 8. Finally, I want to talk about the extended Hypercall interface. So from a guest perspective, this uses the same calling convention, but an extended Hypercall is going to be handled differently within the hypervisor. It's essentially, these are implemented within that virtualization infrastructure driver, the vid, and the root partition. So whenever you invoke a extended hypercall from a guest partition, it's going to forward this off to the root and allow handling there. And last time I looked, there's about 6 of them, so there's not too many and they weren't complex, so we just did code review, so I didn't incorporate this in any fuzzing. All right, so next we want to talk about how do we actually invoke a hypercall and what that environment looks like. So you can only invoke a hypercall from the most privileged guest processor mode. So in the case of x64, this is going to mean protected mode with a current privilege level of 0. And any attempt to basically invoke it when you're not in this mode is going to generate an undefined operation exception. And since Hyper-V does support multiple architectures, all hypercalls must be invoked through their architecturally defined interface. And to abstract this difference away, the hypervisor provides a synthetic MSR for setting up what's known as a Hypercall code page. And in short, we can program this synthetic MSR, and the hypervisor is going to fill in this code page with the architecturally defined. That way you don't have to worry about the details. So in order to set this up, you've got to go through a couple steps. And the code snippet that I have here is coming from the Linux integration services for Hyper-V. And it's really one of the best open source resources out there for seeing how to interface with Hyper-V. So not only does it contain this hypercall code, but it also contains those those VSCs, the components within a guest partition, in order to communicate with synthetic devices. So if you're interested in more attack surface, there's been a couple talks on that. I suggest looking at that. So I want to give a quick shout out to Alex Ionescu, who recently started blogging about creating a Hyper-V bridge. And he did a great job here because he basically covers the same details here, and he kind of took a different approach. Instead of doing this whole interfacing himself, he just used an exported routine that we at Microsoft already implemented, so he didn't have to do these details. But if you are curious and you wanted to create your own driver, you have to set up this interface, and there's a couple of steps. So after you already ensure that you're running on top of a hypervisor and that the synthetic MSRs are implemented, you have to set up this call page. And to do so, you first have to write a guest ID and register with the hypervisor. And the guest ID is simply a 64-bit entity, and this is going to be specified in the TLFS, the format of it. Next, you simply allocate a page of memory. Again, the hypercall code page requires 1 page. And then you're going to program the MSR. You have an enable bit, and the enable bit basically says you should check this first to see if someone else already programmed it. If they did, then a hypercall code page already exists, so we're just going to use that. Otherwise, it's not set, so let's set this up now. All right, so let's look at an example of what this looks like. So the hypercall code page is pretty simple, and so by calling into it, not only can you invoke hypercalls, but you can also invoke the secure calls and normal calls to communicate with those different virtual trust levels. So in fact, to make a secure call, it's basically making a hypercall, but they're programming in what the call code here is. So here, to do a VTL call, hex 11 is kind of the ID to specify for this interface, and same for reversing it. And the reason they include this here is because in a later version of Hyper-V, it's possible that this call code can change. So you don't have to worry about that difference. They'll program it in once you set up that MSR. So the flow for switching VTLs is as such. The normal kernel is going to request some specific services from the secure kernel, and it's going to issue this secure call and vice versa. And if you recall, each virtual processor has an associated attribute to indicate its trust level. So when you invoke this hypercall, all it's really doing is switching the trust level on your virtual processor. And so the routines that I have here, these are really for you to look into. These are exported for you to reverse engineer. The main routine that this VP enter isolated user mem secure mode, it's a mouthful, is the main routine that executes a communication loop. So if you wanted to see how we go about invoking these secure calls, this is where I would go to reverse engineer. And so it sets up what's known as a secure call buffer, which is the format for specifying what we want to do. So This secure call buffer, it's a pretty simple format. You specify what code you want to do, so this is going to indicate the certain operation you want to perform. And then you're going to have various parameters that map to that. And this is what we're going to be mutating, and this is what we're going to be fuzzing. All right, so next I want to look into a couple of restrictions that you might encounter in certain hypercall handlers. So understanding these restrictions is going to be helpful for creating a more efficient fuzzer, because some of these restrictions are going to block you. So understanding how to either get by them or which ones you just can't invoke from a child partition is going to save you a lot of compute power. And so these checks, they'll normally show up, they're implemented at the top of or at the beginning of a hypercall handler. And I'm going to go and show a couple code snippets. And I understand that Hyper-V is not open source, so these code snippets probably won't mean much to you. But a couple months ago, Sar from MSRC Israel, he published a blog post kind of detailing how to get into researching Hyper-V. And he did it from a kind of external perspective. So he showed how to throw it in IDA, started identifying where the hypercall handlers are. So I'm hoping pairing with that information and these code snippets, you'll be able to recognize these patterns and be able to speed up your process. So the first restriction to talk about deals with privileges, and particularly with partitions. And before I show the code snippet, I think it's important to understand a little bit more about their properties. So partitions, if you remember, you have your root partition, you have a bunch of child, and you represent these by a unique ID. So this is going to be some type of 64-bit value. And one interesting thing is these are going to be unique across a Hyper-V instance, but if you do reboot, you can reuse these IDs, but they're all going to be unique on a single running instance. And why it's important to know this is many of the hypercalls, they perform actions against a particular partition. So this is one of the main arguments that you're going to be passing in. So in order to know kind of how to exercise code properly, you need to know how to reference it. So whether you're referencing a partition that you set up on your own or you want to reference self. And additionally, partitions have specific properties that you can query, and you can also modify them. And again, the ones we're interested here deal with privileges and what a partition is allowed to access. And so these privileges are represented by a bit field. So here I have listed every single bit field. These are the privileges that you have. I'm not going to go through each one and tell you what they do, as it is documented in that top-level functional spec. But what is important to understand here is what are your default privileges whenever you set up a child partition. So highlighted here are the default privileges whenever you create a partition. Most of them, they're pretty limited, which means that a child partition, you're not going to have so many hypercall handlers to actually is within your attack surface. One I'll call out here is the access hypercall MSRs. So that one basically says that this partition is allowed to set up that Hypercall page and basically program that synthetic MSR. One interesting thing, though, is if you create a virtual machine using the Hyper-V manager, it'll actually add 3 additional privileges. And this is actually important because these privileges gave us 3 new hypercalls to attack, and we did find bugs in these. The reason they give you these 3 privileges is for enlightened partitions, because this is what enables VM bus and that inter-partition communication. So the root partition, very privileged, basically has access to every single privilege except for the extended hypercalls, because it doesn't really make sense for it to invoke an extended hypercall and then have the hypervisor send it back up. All right, so let's actually look at what this code snippet is. So very simple. We basically set that bit, we're going to pass it into a function which is going to get a reference to our partition and see if we have the proper privilege. So very simple. And this one comes from the Hypercall set logical processor property. So it requires that you have the CPU management privilege. So next I want to talk a little bit about the state of your partition. So partitions, when you first set them up, it's going to be uninitialized. And in an uninitialized state, there's only a handful of hypercalls that can operate against it, such as querying how much memory it has or giving it more memory. So most of the times, if you want to make it useful, you have to make it active. And additionally, there's also checks to make sure that you're either a parent or a child. So let's look at a reference of this. So this is an example taken from the inject synthetic machine check hypercall. And basically that's just going to send in a machine check to this partition. And interesting, and what you need to know about this is it's requiring that you have an active partition and that you need to be the parent of it if you want to be able to machine check it. So it uses the object manager in order to perform this. So you reference your partition ID, and if you notice here, it's coming from your input header. So this is input that you send in, referencing which partition you want to perform this action in. The next one is basically going to reference the conditions that need to be met. So here it's saying that the partition must be active. Other ones are being alive, depositable, meaning that you can deposit memory into it, or it just exists. The next one is going to check the privileges of your current partition. So this is saying whether you are the parent or you want to perform this on yourself, or you must be the root. All right. Next, we have the partition must be the root. So as I mentioned, a lot of these hypercalls, they're limited to a guest, but a lot of them explicitly check that it's coming from a root partition. Because again, as you saw, the vid added additional privileges, so you could always add more privileges, but some of them say you must be the root. And so it's a pretty simple check. It's referenced within your partition structure, and it's basically going to see if it's set or not. Also added a little extra here. There's also hypercalls that must be invoked from the highest virtual trust level. All right, and the last one is your virtual processor must be in a particular state. So what this means, we have a concept of basically saving a memory state and restoring it. So if you want to be able to either save or restore it, you need to ensure that your virtual processor is suspended, because if it's active and running, your values are going to be changing. All right. So now that we've pretty much covered the basics, I want to start talking about Hyperseed. And before we get into too much details, I want to talk of how we deployed it. And so there are a couple different scenarios. So whenever I picked up on this project, this is what Daniel was targeting. He was interested in looking for guest-to-host bugs. So he was running this within a child partition and trying to see if he can get some type of bug either in the hypervisor or in the host. But it turns out that these hypercalls do some funny things, so you can end up pretty much bug checking many different partitions. So you have to kind of monitor this in a very specific way. So whenever I started on this project, I was interested more in finding bugs within the root. So there's a lot more hypercalls that are implemented here, and they have a lot more functionality. But this only applies if you have VBS enabled, because that's the security boundary we're trying to find. So if we can find a bug within the hypervisor, we can now get access to these higher trust levels. And so it's going to be very similar. You're going to be able to crash multiple things, and you have to be very careful when fuzzing from the root, as a lot of these hypercalls will have some abnormal side effects that will just end up killing your host machine before it actually finds a bug within the hypervisor. So I also mentioned nested virtualization. And so I did this mostly for just speeding up our development. I was able to run multiple instances on a single machine, but it does turn out that from this configuration, you could also find particular bugs. So the way it works is when you have a nested hypervisor, when it invokes a hypercall, it's actually going to get trapped to your level 0 hypervisor, and the level 0 is going to analyze this and see if it needs to handle it or if it can pass it back up and let your nested hypervisor handle it. So in this situation, now you can find bugs in your L1 hypervisor, so that's like bringing you one step closer, so more of an EOP, or you can get all the way down to your level 0 hypervisor. And this scenario also brings in a concept that we're not going to cover here, but imagine you had a malicious hypervisor. So now you're getting a little bit more crazy and finding more bugs, but I don't think too many people have looked too much into that concept. So next is targeting specifically those secure codes, or the secure calls. And that's by invoking those two hypercalls for switching your virtual trust levels and sending in that secure buffer. And so for what we're looking here is for crashes within the secure kernel, and also you can end up crashing yourself as well. All right. So next I want to move on to talking a little bit about format-aware fuzzing. So this is where Daniel usually starts presenting. So for this first point here, it doesn't really apply to me, as Daniel had most of this past experience. But he had a lot of success with this technique, so he wanted to extend it to the hypervisor. And so format-aware fuzzing, it's pretty effective to bypass field constraints, and it's easy to scale. So at first, you can pretty much mutate them in a very dumb fashion, and as you start to get a little bit more knowledge of them, you can start applying certain constraints and kind of reducing your sample size down. So one of the bad things about format-aware fuzzing is, one, you need to understand what that input structure looks like. So it's kind of easy for us. We have source code. You guys don't. But it is documented within that top-level functional spec. And a lot of the bugs we found, you could have just pulled that information out of there and created this same setup. It's also worth mentioning that Alex Ionescu, he published what's called the Hypervisor Development Kit, or the HDK, the unofficial one, I should say. And it includes a lot of information that you can just pull in this header and start manipulating these structures as you will. So format-aware fuzzing, besides the resources we mentioned, it's kind of a learning process. So the format-aware fuzzer is more like an agile style of development. So each iteration, you kind of gain more insight into what you're doing. So maybe you just had that dumb fuzzer set up initially and you got a crash. So as you start root cause analyzing or do a root cause analysis on these exceptions, you're going to gain more insight and be able to learn how to apply specific conditions within your fuzzer and make it more of that format-aware. All right, next I want to talk a little bit about our mutators. So this is important for fuzzing efficiency. And depending on who you talk to, your answer is going to be different here. But for us, we just implemented 5 very simple mutators that operate on primitive data types. So the 5 that we have implemented, starting off, we have our random mutator. So again, this is more of a form of generation-based fuzzing. So first we generate some random number, and then we have other ones that are going to operate on this random number, such as a sliding mutator. And the sliding mutator is essentially a circular shift, and it's just going to shift your bits around. The third one is very similar to the sliding mutator. We're going to swap halves. The reason we like this one is because it keeps your alignment. This one probably most people know of, bit flip. So now we're just going to start flipping certain bits, and we're going to specify which bit we want to flip. And the more important one and the more interesting one is this mask mutator. So if you kind of look at how these primitive data types are, you realize a lot of them are sparse. So by masking off certain bits, you can basically erase them and get more kind of looking like these synthetic MSRs or looking more like pointer types. And so with these 5 basic primitive types, we can create a dispatcher and apply more random logic and more complex logic to it. So essentially we take in a random byte, and that's going to determine which one of these operations we're going to perform. And this brings a lot of randomness to the equation. So now we want to look at some of the components that make up our fuzzer Hyperseed. And we've already discussed kind of how we invoke these hypercalls. We have this proxy, which is just a kernel driver. And we talked about the 5 primitive mutators. And this is essentially all we need in order to get more complex logic and start implementing specific mutations for hypercalls. So here we use a divide and conquer way to organize mutations into a stack. So we have some generic mutations. So these are going to help mutate things like that call code or what type of calling convention we want or the class of it. And then we also implement a default hypercall mutation, which is very coarse-grained. So it's essentially going to break up your buffer into keywords and mutate each one. So that's as dumb fuzzing as you can get. And this is represented by our C-base mutation class, which is our default for all hypercalls. So next we have classes for each hypercall. And why do we need specific ones? Well, this is where that format comes in. Each hypercall takes in a particular data structure, and the data structure, all the fields are going to be different. And they have different meanings, such as being a partition ID, virtual trust level, or some reserved field that must always be 0. So we can essentially enlighten our mutations in order to narrow down our sample size, which makes our inputs essentially survive basic checks that would normally get blocked with basic dumb fuzzing and get a little deeper in the code. So this is kind of an example of how we implemented this within our framework. So here we have a specific hypercall mutation. This is for the flush virtual address space hypercall, which essentially just invalidates all virtual TLBs and entries that belong to a specific address space. So on the left here, I have what I pulled out of the top-level functional spec, which just tells you exactly what the arguments are. So there are 3 parameters. You have your address space, flags, processor mask. And the flags is a keyword that actually acts as a bitwise composition of several binary options. And so only the lower 3 bits are valid, where other bits are reserved to 0. So the fuzzing efficiency for this specific hypercall will be remarkably boosted by enforcing this format rule. We also have several macros just to kind of help make our code a little bit more neat. And the BM macro, which stands for basic mutator, is a wrapper. And basically what it does is you can directly apply this on any primitive data type, and due to some C++ template magic, it'll manage to find the exact type that you need. All right, now for the cool part. So now that we understand our fuzzer, which overall is a very basic fuzzer, and the curious thing is, what results do we get? So when you think of Hyper-V, it's supposed to be a pretty hardened target. This is what runs Azure. So if you have a bug in this, and we offer up to $250,000, it means serious business. So I wasn't expecting to find much, but it turns out we found a good bit. So overall, we started this a year ago, and we got 16 findings. Running a little behind on time, so going to speed up. We found 8 escalation privilege or remote code execution, and 8 DOS. And then 2 of these qualified for the Hyper-V bounty, and 7 qualified for the whip. So let's see how much money we would have made if we reported these as an external. So first, here's kind of an outline of where these components were found in. So the red vector is going to indicate that this was basically code execution, whereas the blue was DOS. And on the y-axis, this is going to tell you which scenario you deployed this from and where we got a crash in. So for instance, if you look at the left, one of our bugs, we had an escalation of privilege from our root VTL0, and we got a crash in some hypercall handler in the hypervisor. You'll notice the one that kind of redirects itself, so that's an interesting one where it ended up DOSing. So for the 2 that qualified for bounty, one was a remote code execution in the host, so this would have gotten you a $200,000 if you just reported the bug without an exploit, and one was a DOS. And we're going to look at the DOS a little bit later, and that would have netted you $15,000, and it was very easy. Then we also had a bunch that qualified for our Windows Insider Preview bounty. So 2 were specifically within hypercall handlers, and 5 of them were within those secure service calls. All right, so I'm going to talk a little bit about a bug that was patched last Patch Tuesday, which was unfortunate because I reported this in July of last year, so that kind of shows you the timeline it took to patch this, even though it's very simple. So we're going to work backwards. So this is kind of the call stack that I got whenever we hit this issue. So I highlighted the fields that are important here. So you look at which hypercall it's in. So this is the get VP index from your APIC ID. We see that we basically have an out-of-bounds read, so we have this access violation. And if you look at what those registers are, RSI looks like a very valid pointer. But if you look at RDX, this looks like a huge index into this, which is why it's causing. So let's see what's going on here. So this hypercall is very simple. It's a repeat hypercall, and you specify a partition, your target VTL, and if you see within where it describes the parameters, the padding of 7 bytes, these are reserved fields that must be 0. And then we specify an APIC ID, and so this is going to be your repeat, so you're just going to specify a big array, and you're going to have various APIC IDs for the number of processors you have. So this is what our mutation looked like. So it was very simple. Essentially, we take that input structure that we just talked about, we enlighten it to give it a valid partition ID and a valid target VTL, and we make sure that those reserved fields are set to 0. And then we basically randomly generate a certain number of this array, which specifies our hardware IDs. So if we go look at the restrictions, one of the interesting things is that this had the start virtual processor privilege, which is, if you look back, it's default for all guests, so this makes it a guest to Hypervisor DOS. And we explicitly check that those fields are 0. All right. So the bug. The bug was very simple. So here's the snippets of code that you need to worry about. So the first one, basically, we have this concept known as a partition per level context. So each partition can have multiple contexts, and they're going to be associated with each virtual trust level. And each virtual trust level is going to maintain which virtual processors are enabled, and that's represented by this virtual processor set that I colored in blue. And this is essentially a bit set, so they're just trying to optimize your space you have there. The APIC ID, which I represent in red, this is what we pass in, so this is user controlled. So we go into this bit set member, it's going to do some type of bit shift. So if you remember, you saw that RBP was 41, 41, 41. So it's applying a bit shift of 6 to this, which brought it down to that 1050. And then we're simply going to index this into that virtual processor set. So the virtual processor set is a static array. So this is just simply an index out of bounds. Very simple. And it's a one-line fix. Now we just need to ensure that we won't go out of bounds. So this would have been very easy if you just picked up the top-level functional spec, programmed as is, would have found a nice little bug. All right. So now we're going to talk about the future. Essentially, keep improving this, adopt coverage-guided fuzzing, so we now have Intel PT working within the hypervisor, so we can start working with getting an AFL set up on this. We'd also like to get a little bit more details after bugs get patched, and maybe open sourcing. That one might be a little bit more difficult. Some acknowledgments. I'd like to thank MSRC and the team I was working on at the time for allowing us to, one, come out and present this work, and also the Hyper-V development team. These guys are super elite, super knowledgeable, and they are great to work with. So as promised, I do have an appendix of some past research, so this should be published at some point, and some useful public resources for you to go investigate. So now we will do Q&A.
Oh. Thank you very much, Shawn. How about a round of applause for Shawn? If you have any questions, now's the time.
Can you tell us a little bit about your crash collection? Functionally, there are two potential crash dumps, call stacks that could be going on. There's some potential for complexity there.
Yeah. So whenever we set out for this, we weren't expecting to find much, so we didn't actually do any scale to this. So we actually just ran them from our test machines within our office, and I just set up a kernel debugger to them. So a lot of work for actually scaling this in the future. And yeah, we had a kernel debugger set up on each one of those, which is why I showed the deployments. So we had it on the root partition and the hypervisor.
Was that out-of-bounds error or bug just a one-line fix? Why did it take so long? Maybe they just didn't handle the error at all.
Yeah.
Didn't expect it.
Good question. So they handle, whenever someone internally finds a bug, they handle a little bit differently. They kind of take their time with it to ensure that it gets pushed out everywhere. So since this affected the hypervisor, they needed to ensure that they updated the Azure fleet before initiating a bulletin. And additionally, it was supposed to be fixed back in December. I'm not sure what happened to make it get pushed out 3 more months, but somewhere some communications were lost.
Some other questions? Okay, doesn't seem like it. What's your last chance? No one?
Cool. All right, thank you, everyone. Hope you enjoyed it.